Good afternoon, everyone. My name is Tony Roskilly. I'm Professor of Energy Systems at Durham University, and I lead the EPSRC Network Plus on hydrogen fueled transportation. This webinar is organized by Network H2, and it's part of a series of webinars looking at different aspects of hydrogen research that's related to the transport sector. This week, we welcome two speakers who will be presenting their findings of two projects that were funded by the network, which were investigating the techno-economic feasibility of hydrogen fuel transport and the optimization of hydrogen refueling locations for road freight. We'll go on to the next presentation by Dr. Christa Searle. She's an assistant professor at Herriot Watt University, and she's going to present on the analysis of a strategic hydrogen refueling infrastructure. Christa is in the operations management and logistics team at Herriot Watt as a member of the Centre for Sustainable Road Freight and the Centre for Logistics and Sustainability. Research interests are within the fields of logistics, sustainability and behavioral modeling, with the application of operations research, computer simulation, agent-based modeling and data analytic techniques. Christa is also involved in the teaching of business analytics and big data analytics. So over to you, Christa.
Well, thank you, Tony. Thank you very much for the introduction. All right, well, so I'll be sharing on the project we did, which is called the ATHENA project. And it's all about the analysis of a strategic hydrogen refueling infrastructure, where I worked on it with a few of my colleagues at the Centre for Logistics and Sustainability at Edinburgh Business School, Herriot Watt University. Right, so the aim of this entire project was how do we start, the challenge we're facing is how do we deploy a hydrogen refueling infrastructure, and specifically focusing on heavy good vehicles. And the questions that we aim to answer through this project were questions such as, what are the refueling demands for heavy good vehicles? So that's our starting point. And from there to understand what is the minimum number of refueling stations required to serve this refueling demand of hydrogen. Then also understanding where should these refueling stations be located? How big should they be? And finally, what is the best hydrogen dispense and delivery model to follow? So the aim of this project was to analyze certain strategic corridors in order to determine and finally also recommend this hydrogen refueling infrastructure for effective deployment. And in order to do this, we kind of formed a model and framework with a focus on a concept demonstrator. So our concept demonstrator and the scope of it was specifically in focusing on the UK or Great Britain, focusing also specifically on the north of England, a specific region called the Northern Powerhouse 11. So, I mean, currently we know that there aren't any existing hydrogen networks for road freight. And our idea is to translate the diesel demand we have in heavy good vehicles to a heavy good vehicle demand in hydrogen. But of course, with diesel, there was this organic growth of the diesel refueling network that occurred over time. And now, with Network Zero goals, we don't have the luxury of time. And also, we have the opportunity to actually create an optimized network. So the idea of our framework and model and the research we performed in this project was to determine an optimal network for hydrogen refueling infrastructure. And the idea is that the model output would then give us the optimal number of refueling stations, the locations, capacities, and type of refueling stations, and also the supply configurations to these refueling stations, an idea of what the overall cost might be. So this is just to capture the framework, and it has three definite phases. And the first phase focuses on the demand data analysis. So in this phase, we just consider what is the demand of heavy good vehicles, where does the demand occur, and we consider certain input, specifically the raw freight logistics data, as well as data on existing and potential refueling sites. And once we have that and we can map then this analysis of the hydrogen demand, we move on to the optimization model and analysis, which is our second phase. And this work on a very strategic level, where strategically we can determine where should the refueling stations be, how large they should be, and exactly where they should be located, and how hydrogen should be supplied to them. And we consider input data additionally, such as the data on the production and storage facilities, the delivery and dispense technologies. And from this optimization model output, we will get a hydrogen refueling infrastructure network design. Then we take it to a third phase, and we are able to perform certain experiments, do certain analysis, add some stochasticity to it, look a bit more perhaps on the operational side of things, and where we work in the optimization model. On the second phase, with a more deterministic approach, we can now add this uncertainty in the agent-based model, and from there it also assists us in providing a robust hydrogen refueling infrastructure network design. So I'll speak through all three phases and how we approached it in this concept demonstrator, focusing on the Northern Powerhouse 11. So the first phase is this demand data analysis. We started off by collecting various input data. So the first was warehouses, specifically in Great Britain. We had over 1,700 records with different features, which we cleaned, filtered, and used around 626 records. So key things here was exactly where is the warehouse located, and also what is the total area or the size of the warehouse. And the reason why the size or total area is important is because we assume a correlation between the total area of a warehouse and its capacity to be a refueling point. And then we also only considered records, so warehouses with a total area that's greater than a certain size, and we ended up with about 382 records, so 382 warehouses. And here I've plotted them on the map also for you to see, and we can clearly see again, here is more or less where the Northern Powerhouse 11 is and the area of focus, and we can clearly see that industrial clusters. Then we also considered data on service stations. So we gathered data about 291 service stations, specifically focusing only on heavy good vehicle service stations, also exactly where they are located within Great Britain. And here's a plot of all these different service stations. And the third type, so these are all demand types and places where demand can occur for heavy good vehicles, is ports. So we had a set of ports as well. Again, cleaned, filtered the data. The most important thing was just where they're located, and we're able to map that at the end of the day, as shown here. And then finally, when we're looking now just at our area of concern, which is the north of England and the MP11, so we've identified where demand may occur. So for heavy good vehicle demand within that MP11 region, we're sitting with about 213 demand sites, of which there's 158 warehouses, 43 service stations, and 12 ports. And this is roughly about 40% of the total heavy good vehicle demand in Great Britain. So that is just currently what you can see from the diesel side. And then another interesting aspect here is considering the logistics data for heavy good vehicles. So the first thing is just understanding currently with fuel demand for heavy good vehicles, the diesel equivalent in Great Britain, what is the total, what is the monthly fluctuation that occurs for us to be able to translate it into hydrogen terms. And the second interesting piece of data that we have here and that we received from Transport for the North is about the freight data per road link in the north of England. So that translates to how busy a road can be or a road segment can be during any time of the day. And here's a map of that, and it shows what we call the heavy good vehicle actual flow data. So for each one of these road links, you can see what the flow rate per hour can be of heavy good vehicles. And I'll show later why this was important for us and how we used this data also. So once we have collected all of that input data, we now move to a phase where we convert the diesel demand, fuel demand, into an energy demand so that we can speak in terms of energy terms. Then we start distributing this demand between all of those different demand sites, so between all of the warehouses, service stations, and ports we've identified. So first we need to consider the distribution between the demand site types. Very interesting that in warehouses, for example, that is where 75% of the diesel is currently uplifted for heavy good vehicles. So in the way that we distribute the demand now for hydrogen, it would be in a similar fashion. Then we used that heavy good vehicle actual flow data from Transport for the North, and we calculate a popularity estimate for each of these demand sites based on this flow data. So of course, where a road is busier and there's more trucks flowing, there will be a greater demand. And then we distribute this overall demand between all of the warehouses proportional to the total area. So a larger warehouse will have a larger demand, as well as the popularity estimate. And then it's distributed amongst ports and service stations according to this popularity estimate. So after we've now distributed the demand, we can map a spatio-temporal, just a geographical map of the hydrogen demand during 2 phases. And we've considered here what we call a rollout phase. So that's about 5 years from now, as well as the mature phase, which is roughly in 2014. And here's an example of this map. So on the left-hand side, this is what is estimated for rollout. And we're making the assumption that there will only be about 0.1% of the current diesel demand for heavy good vehicles would have been converted to hydrogen. So considering that, this is what the demand would look like, and it's mapped between different demand sites, which are also clustered together. And then on the right-hand side, it is looking at the mature phase. So that is roughly in 2040, where we've assumed about a 50% conversion to hydrogen for heavy good vehicles. And then this is how the demand would spatially be distributed around the area of concern. Right, so after we've mapped that an analysis now of this demand, we can move on to the optimization model and analysis. So again, we start off with our input data. And input data here specifically start off with production facilities. So we assumed that we used 5 green central production facilities. And then, of course, we need to consider the different delivery and dispense technologies. So if we look at this, illustration here, you'll see there's primarily 2 ways in which hydrogen can be produced and get to a certain station. First is with central production, so that is often called also off-site production. So that can be whether it's green or blue hydrogen. For this case specifically, we only focused on green hydrogen. So when it uses central production and it's from off-site production, then it needs to be delivered to the hydrogen refueling station. And for the case of this specific project and concept demonstrator, we only considered that it would be delivered in gaseous form in tube trailers. Then the other option, apart from being off-site hydrogen supply, is the on-site hydrogen supply, which is also the local production, where there's an electrolysis or an electrolyzer stationed at the specific hydrogen refueling station, and there's no transport then necessary. All right, so starting then off to look at the actual model. So the optimization model focuses, and its underlying goal is to minimize cost. And there's 3 primary cost factors. The first is looking at HRS, stands for hydrogen refueling station. So that is, what is the cost to set up a station, and what is the storage cost involved? The second feature is the offsite, so that is for centralized production. If you use that, what is the transport cost, and also what is the unit production cost? Then finally, for on-site or localized production, we consider the setup cost of having that electrolyzer at the hydrogen refueling station, as well as the unit production cost. So just to also include and show you the decision variables. So decision variables is basically what we want the model to give us as answers. So the model will tell us at the end of the day, for each scenario that we perform, it will give us the location of each hydrogen refueling station. It will give us the capacity of each of those hydrogen refueling stations. For each station, it would specify whether it should use on-site and or off-site production supply. And I'll speak later on why we included the and or, where a station can have both on-site and off-site. And that was just for this concept demonstrator. And it also includes the quantities for both. Then, if it recommends that a certain hydrogen refueling station is on-site, it would also display or recommend the size of the electrolyzer. For off-site, it would give you from which centralized facility it should be supplied, and also the number of tube trailer deliveries that will be required. We also have certain constraints built into the model, and I've just listed a few. So the first thing is that we can merge the demand from sites within a specific range from each other. So for example, if you have an area where there is, for example, 4 or 5 warehouses very close to one another and within a certain range, then it can merge the demand so that instead of having those 4 or 5 hydrogen refueling stations in very close proximity, it might only prefer, due to the system which is trying to minimize the cost, to have only one hydrogen refueling station. And the specific range that we're working with is something that's built into the model. That's an input parameter, so we can decide to vary that range. So we work on, for the mature phase, about at the 2 kilometer range from which it can merge. Basically what that means is, worst case, if a truck were to refuel at a previous, where it would have refueled previously, having had diesel, it might have to go, worst case, out of its way, roughly 2 kilometers to refuel for hydrogen. Then the second constraint there is that this aggregated demand may not exceed the maximum capacity of a hydrogen refueling station. The third constraint there is that all demand needs to be satisfied by at least one hydrogen refueling station. So in other words, no one gets left behind. All the demand that would previously have been satisfied will get satisfied by one or more hydrogen refueling stations. Again, then all of these hydrogen refueling station demand must then be supplied by either the on-site and or the off-site production. We also have certain limitations in capacity set for on-site production maximum capacities, and we're varying it between, I think it's 1, 5, 10, 30, and 50 megawatt electrolyzers. Then when it comes to this tube trailer deliveries, so where the hydrogen is delivered from the centralized production facilities to the actual hydrogen refueling stations, there's a maximum of 3 deliveries that can occur per day per hydrogen refueling station. So considering all of that, here is what the model showed us specifically for the rollout phase. So again, this is 2027. And I previously showed kind of what the demand would look like during that stage. And it recommends having 8 hydrogen refueling stations. So here you can see the green is where these off-site production hydrogen refueling stations would be. The blue indicates the supply points. So this is the centralized facilities. And the red ones were previous demand points, which it is now made inactive, and it has pushed that demand to one of the other hydrogen refueling stations that exist now. And then this transport link in orange just shows from where each of these hydrogen refueling stations that are selected will be supplied from. And at that stage, remember, this is when it's about 0.1% of the current heavy good vehicle demand that will be converted to hydrogen. We're looking at a largest station of roughly 850 kilograms per day, and the smallest about 70 kilograms per day, which is fairly small, and an average around 265. Interesting enough, the model recommended that, or it gave preference for only off-site production supply to all of these hydrogen refueling stations in the rollout phase. Then we will look at the mature phase. So this is estimated for 2040. The model gave the output of having 189 hydrogen refueling stations, with the largest one being just over 23 tons per day, and the smallest about 700 kilograms per day, average 5.5 tons per day. And if we consider the configuration of the hydrogen supply, it indicated that there's approximately 1% that it would recommend goes only on-site, so that is localized production, whereas 24% is only off-site, and the remaining 75% is a combination of on-site and off-site. So it was interesting to actually look into this, because we've realized that there's a binding constraint that occurs here, and why we see this high figure where it has both. And we did some further research into that. So just again showing on the map on the left-hand side, where blue is the centralized production facilities, and it shows the transportation links to the different hydrogen refilling stations where it will deliver to. Purple is when a hydrogen refilling station is on site and localized production, and green is when a hydrogen refilling station uses centralized production, so it has off-site production supply. So looking into that binding constraint of why there was such a high figure and high percentage using both on-site and off-site, we investigated the situation when we have only on-site versus only off-site production supply to refilling stations. And in the case with only on-site production, it actually increases the cost from the base case to about 18.11%. And in the case of only off-site production, it decreased the cost to by roughly 32%. But the problem there is we removed the limit on the number of tube trailer deliveries per day. And what happens is the average number of deliveries per day starts exceeding 9, which is not necessarily feasible. And basically what we found from this and can derive from this is that the system optimality is limited by the number of deliveries per day, so by what the tube trailers can deliver per day to a hydrogen refilling station, which also shows that there's an opportunity for pipelines and to investigate that further. Further investigating this increase in the number of daily deliveries. So you'll see within this figure, at the bottom axis, we're looking at the number of daily deliveries allowed per hydrogen refilling station, increasing it from 2 to about 8. And then you'll see on the left-hand axis, that is the portion of refilling stations, where this dark blue is only off-site. And then this green is when it used both on-site and or off-site. And this little pink slit at the top is when it used only on-site. What we see clearly is when we start increasing the number of daily deliveries allowed, then it immediately increases, although not necessarily linearly. As we increase the number of deliveries allowed, it starts switching over some of the stations to become only off-site. And the reason also why I said it's not necessarily linearly is because we also measured here, you can see on the right-hand side, the average number of daily deliveries. And as you can see, when the number of daily deliveries allowed is 2, the average number of daily deliveries is also 2. But when we start increasing it up to, for example, 8, we actually see that the average number of deliveries is below 6. So therefore, it doesn't necessarily increase linearly. And what we can see here, and also, if we'll see will happen, is if we do not necessarily allow the on-site and or off-site to occur together or simultaneously, that the majority of the sites will be only off-site, and there will be a small portion that will be only on-site. All right, so from here, we can move on to the agent-based model and analysis. And again, this is the phase where we can perform different experiment scenarios, test uncertainty or add certain stochasticity to it. And I'm going to share just one of the analysis that we looked into here. For the agent-based model, we use the optimization model that we just looked at beforehand as the input. And now we have agents. And our agents that we have here are the different stations, the hydrogen refilling stations. We also have the centralized production facilities, and we also have the tube trailers to basically model and mimic how these deliveries will occur, what the timing would look like, and things like that. So again, we can perform certain experiments and test certain scenarios. So one thing that we did is we tried to capture the stochastic demand profile of each station. So what happens in the optimization model is deterministic. So you assume that the demand over a year is distributed equally amongst every day of the year and every hour of the day. Whereas now in the agent-based model, you can add the stochastic demand profile, where you can say, for example, between 8 and 10 in the morning, there might be a large peak, which decreases, and then again a large peak in the afternoons, or whatever the case may be. And we can also then capture any unserved demand. So what happens if a station runs out of hydrogen, and it cannot necessarily serve the demand of a truck that wants to refuel? Where should that truck go to? What happens if there's maintenance, or what happens if one isn't available? What happens to the system in its entirety? And we can actually look and visualize this emergence that occurs. And we also, one thing we did here is trying to vary the capacity of the hydrogen refilling station to identify what is the actual required size, because there's naturally a cost to storage on the at the station, and trying to see what happens if we decrease that cost slightly. Here, this is what the model would typically look like. So you will have all of the different stations, which are noted here in little yellow icons, and the red icons are hydrogen filling stations that are in need or needs to be replenished. And you have little trucks. This black little truck there is now filled. It's on its way to deliver hydrogen, and the white little truck still needs to be filled, and it's trying to go back to refuel and replenish again. And blue icons again is all of our blue and green is all of the supply points, all of the centralized production facilities here. So one of the scenarios I was talking about where we try to vary and trying to gauge what the size of the storage should be at a hydrogen refueling station is we start varying the capacity of the station in terms of what the size should be of storage. And in doing so, trying to capture what is the cost savings, but also what is the unserved demand. And we can see here the savings as marked in blue or highlighted in blue. And as we start decreasing the hydrogen refueling station capacity, there's a definite increase in cost savings, marked here on the left axis in blue. The problem, though, that we see here is in pink, we have the unserved demand. And again, as we decrease the hydrogen refueling station capacity and we have that cost saving, unfortunately, we're also increasing our unserved demand. And naturally, there's that trade-off between the savings and the effectiveness and how this should be managed. I think that more or less sums up the agent-based modeling side as well. And just to end off, I think we did very interesting work and really enjoyed working in it. And so that it actually led on to another project that we did now with on a strategic innovation fund project for discovery phase, which is a multimodal hydrogen refueling strategy for the north of England. And we did that now in partnership with Northern Gas Networks, Transport for the North, Element Energy, Rees and Eversholt. So if I say we did it, it's obviously with Durham University as well as part of this network H2. And for this project, we then took this framework that I just explained to you and showed you in this ATHENA model, and we expanded it to include multiple modes. So we looked at adding buses, refuse collection vehicles, port handling equipment, and then also we looked at adding the pipelines and allowing for the pipeline network extensions in the mature phase. And this then further led to another project that we just put in a proposal for, which is the Strategic Innovation Fund, the Alpha phase, where it will be this pipeline hydrogen for multimodal mobility for the North in partnership as us with Network H2, with Herriot Watt and Durham University and Northern Gas Networks, Transport for the North, Element Energy, looking at further additional modes such as airport and rail, and also looking at refining this ATHENA model further, looking at simulating different time steps. I think that's more or less a wrap from me. Thank you very much.
Thanks very much, Christa. Excellent presentation.